The last tool that we're going to look into is statistical process control. Okay, it's going to be for attribute data. So before the X bar and R charts, both are done when I have continuous data that I'm measuring. Right, I'm taking each part and measuring the height or the weight or the distance or how many milliliters, whatever kind of continuous measure. Okay, now we're going to use discrete data. You guys remember discrete data? Discrete data is the one that it's only a 0, 1. It's a yes or no. Okay, and basically you're saying that you have good products or bad products. Okay, so you take a product, don't measure something, you're just going to say it's good, it's good, it's good, it's bad, it's good, it's good, it's good, it's bad, and so forth, so on. So in this case, we're going to use the P chart. Okay, so the P chart, P stands for percentage. Okay, and that's or proportion. I like percentage more, it's easier to remember. So percentage of items that have a problem, that's the P chart. Very, very clear and easy to remember. So how do P charts work? The data is a lot simpler than the X bar chart. I only have the samples. In this case, we capped onto 15 samples, but we collected data about 100 data points in each sample. So you can see that the number is a lot higher. But then the only data that I have is how many of them were defective. Okay, so 15 samples, 100 observation in each sample. These are the number of defective products in each sample, and I got P, which is the percentage, right? It's just the defectives divided by N. It's give me P, which is the percentage of items that are defective, right? And I have the total observation number, and I have the total defective number, okay? So first thing, I have to calculate what is called P bar. P bar is the average line, right? The average of the percentage. So I'm just taking the 55 and divided by 1500. Where the 1500 came from? The sum of observations. So I had 55 problems. I collected data about 1500 different items. So if I take 55 divided by 15, voila, I get the average percentage, which is 0.037 or 3.7%, right? This is P bar. The kind of trick here is to calculate the standard deviation of P bar. And there's this nasty formula here that gives us the standard deviation. So it's going to be P bar times 1 minus P bar divided by N and all that squared. Okay? So we know what P bar is. We just calculated. And we know what N is. Do you guys remember what N is? And hopefully you all said at the same time the number of observations in each sample, right? So in this case, we have 100. Yes, I know that you guys are not all together. You're watching this, a video probably alone in your room, but I'm talking like I'm talking to all of you at the same time. So calculate the standard deviation of P bar. Okay, put in the formula, do the math, 0.0189. So how to calculate upper and lower control limit? You just calculate as P plus or minus, and there's this Z here. Okay, why did you put a Z there? Well, the Z is just asking us the number of standard deviations. Usually, most of the problems are going to use 3. Okay, so just use P bar plus or minus 3 standard deviations, and you're going to be good most of the time. Okay, if the problem asks you another one, then you can do it different. Oh, it's going to be 0.037, which was the P bar, plus or minus 3 times the standard deviation. Okay, it worked fine for the upper control limit, but the lower control limit was a negative, right? So what does that mean, Dr. Martin? Well, it means that you cannot have a 0.01 negative percentage. You cannot have a negative percentage. You either have a 0 or 100. So you truncate that to 0, right? So it's going to be 0, your lower control limit. You can go less than 0 on the percentage. So how does this where does it came from? You have 1 to 15, the samples that we took. We have the P bar for each one of them. Going back here, these are these P bars. Okay? So those values, from 1 to 15 p bars, are the ones that I use to plot into this chart. So these are the numbers. These are samples, central line, upper lower control limit. So question of the day: is the process under control? Yes or no? Awkward silence. It is, right? It is, right? Because there's nothing outside the control limits. Okay, so the process is under control. Finally, just some kind of other situations that companies might face when they're doing statistical process control. We talked about one of them. It's when one dotted line exceeds the upper control limit. Here talks about some other ones. For example, this is what you expect to be up, down, a little bit up, a little bit down. That's okay because you expect it to be randomly ups and downs, but mean centered and all that. This one, you can see there's something happening, right? So you were good, but then a lot of data points lower than the lower control limit. You expect data points to be lower than the central line. So you expected some data points to be here, but some of them have to be up there too, right? So it's only down, it means that something is pulling the average down for some reason, right? It's not going up again. Here is just showing kind of a abrupt change, although it's not outside the limit. It's going up or down for kind of some reason. You better investigate. And this is the one that we're talking about, right? Something that goes outside the limits, upper or lower.